This is our first video in rotational kinematics. Now, for this entire unit, the learning goals I want you to be able to do will be to solve circular kinematics problems, understand what angular frequency is, explain what causes circular motion, and be able to solve problems that involve both friction and circular motion. All right, so to start off this first video, we're going to talk about what exactly circular motion is. Now, the motion we have studied so far is called translational motion. And this means motion along a path. Now, this path can be a curved path, it can be a straight path, it could be any kind of path you want, but it has to be along a path. Circular motion, on the other hand, occurs when an object spins around an axis. Examples for this include planets, solar systems, obviously wheels, a lot of amusement park rides, anything that if you can find an axis and see where something is spinning around it. So what this means is that we need to identify the axis of rotation. And this is just simply a line for which the rotation occurs. So let's say we have something that looks kind of weird, like this object right here. This object is rotating, and the axis of rotation is this line right here. And we can see that the direction of rotation here appears to be counterclockwise, like that. So what's kind of cool is, even though this thing has an odd shape, if we were to study a single point on this, even though this is an odd shape, this point would follow a perfect circle. And we can do this for any point. And every point, and obviously there's an infinite number of points on this shape, but every single point will follow a perfect circle. So, there have to be conditions for this, obviously. The object must be rigid. So if this were made of rubber, and as it starts to spin, you might imagine it starts to stretch a little bit, then those points would not follow a perfect circle. But as long as this object is rigid, that means it doesn't stretch, all the points in the object will make a circle as they rotate around this axis. And again, it doesn't matter what shape the rotating object is. Now, when we talked about kinematics, we discussed displacement. And you remember that displacement we used was a delta x, which meant the final position minus the initial position. Well, for rotating bodies, we need to talk about their angular displacement. And what this means is that we're going to use angles instead of distances or positions. So let's take a look at an example here. If we have a CD, that spins through 1/4 of a turn, every point on the CD will move through the same 90-degree angle. So if I were to make a Cartesian coordinate system, and if I were to allow this object to make a counterclockwise rotation, a point right here we could say is its initial angle. So I'll use a theta and a theta naught. And then as this spins, if it spins through 1/4 of a rotation, this point will end up here. And that will be its theta. So we can see that we have its initial angular position and its final angular position. And notice that no matter what point or no matter how far away I get from the axis of rotation, all points will turn through the same angular displacement. Which is kind of cool if you think about it. Um, everything on this line right here moves through the same angular displacement. So again, on the CD example that I showed you before, each point moved a different linear distance. So let's go back here and take a look at this. Notice that the red line travels a farther distance than, let's say, the blue line. They all move through the same angle, but their linear distances are different, with points farther from the axis moving the greatest linear distance. Now, for this reason, we need to define a set of variables that are analogous to displacement, velocity, and acceleration. And for this, we're going to use angular measurements instead of linear measurements. We could do this with the linear measurements. However, it would become very, very mathy, very, very quick. So instead of using a delta x, we're going to use an angular displacement, delta theta. So let's take a look at, again, another circle here. We're going to be looking at a lot of circles for this unit. And let's say I have a point right here. Changed my mind. Let's say I have my point right here. There would be a displacement vector right here, and I would call this displacement, let's say, r. Now let's have my point make a counterclockwise rotation up to this point. Notice that the length of r stays the same. However, its direction changes. So for right here, I would have an initial angular position, and then for right here, I would have a final angular position. My angular displacement then would simply be the final angular position minus the initial angular position. Now, with the linear kinematics, we had to worry about direction since we had a lot of vectors. And here we do have direction as well. And basically, what we're going to say is that everything that moves counterclockwise is positive, and everything that moves clockwise will be negative. So if the angular displacement is counterclockwise, that's going to be a positive angular displacement, and if the angular displacement is clockwise, it'll be a negative angular displacement. Now, we talked about these angles. We also need to be able to measure them. And to measure angles, we are going to either use the degree or the radian. Experimental physicists tend to prefer degrees. All protractors measure in degrees, and it's real easy to measure a degree. Theoretical physicists tend to prefer radians. It makes the math look nicer. It makes the math easier. And radians would be easy. Well, radians are just easier to understand in many ways than degrees. So what I'm showing you right now is something called the unit circle, and this is something that you should have learned in math. The unit circle, basically, we take the circle and we break it up into different sections. Once completely around the circle equals 360 degrees, or 2 pi radians. Half a circle is 180 degrees, or pi radians. And we can use trig here. We can also use sines and cosines. If I were to plot this point right here, I would see that it forms a right triangle, which means I could use sines and cosines as well. And using the sines and cosines, I would find that, if this is my theta right here, sine of theta equals opposite over hypotenuse. Well, for all of these, the hypotenuse is 1. That's why we call it a unit circle. A unit means 1. So if sine of, let me put a number in here. So sine of 30 degrees equals the opposite over 1. Well, if we look at the opposite is a y value. And we would find then that sine of 30, well, if I were to do algebra with this, I'd have 1 times sine of 30 degrees. We would find that that equals 1/2. And that's this value right here. The x part, well, that would be cosine. We could see that cosine of an angle equals the adjacent over the hypotenuse. Again, the hypotenuse is 1, so we would have 1 times cosine of 30 degrees. I keep trying to put in theta here. 1 times cosine of 30 degrees. Well, that would equal radical 3 divided by 2. And just going through here, doing all of these points using sines and cosines, we can figure out all of these values. So this just gives us handy ways of estimating these different angles very quickly. And some math teachers will make you memorize this. I'm not going to make you memorize this unit circle. But it is a very helpful tool. So looking at these, then we see that we have these radians, like 5 pi over 6, 7 pi over 6. I mean, we want to figure out where those come from. So here's how we define the radian. If I have a circle, I always like to put my Cartesian coordinate system on the circle. And let's say I have my position vector r turning from here to here. Well, on the leading edge, we have this curve here that we call S, which is the arc length. And it would be turning through an angle. Actually, I'm going to rename this. I'm going to call this delta theta, because I've got my theta initial and my theta final. And the way we would define the radian is we would say that this angular displacement, delta theta, equals the arc length, S, divided by the radius, r. Notice that means that the radian is a ratio. And it's the ratio of the arc length to the radius. So that means, first off, they both have to have the same units. The arc length needs to be in meters, the radius needs to be in meters as well. Or centimeters and centimeters, inches and inches. It doesn't matter, but they have to have the same unit, because arc length, or I'm sorry, the angular displacement is a ratio. Now, we want to be able to convert back and forth between radians and degrees. And from the unit circle, remember that 360 degrees is the same thing as 2 pi radians. Or if I were to divide by 2, 180 degrees is the same thing as pi times radians. So that means that if I want to calculate the radians, it would equal the degree multiplied by pi over 180. And likewise, to get the degree, that would equal the radian times 180 over pi. So if you know what the radian is, plug it in here and do your math to get the degree. And if you know what the degree is, plug it in here, do your math, and get the radian. That concludes video 1 for this unit.